Listo, estamos en vivo.
Ok. Buenos días a todos. Vamos a esperar un par de minutos antes de comenzar. We're going to wait for a couple of minutes before we start. Welcome, everybody. Okay, I think we can start. So welcome, everybody. Today is really a celebration for us at the Physics Institute. We have the honor of having Professor Carl Wieman from Stanford University for our colloquium. Professor Wieman did many things during his very excellent career. One of them was making a very careful precision measurement. A measurement was an example of how the precision measurement was supposed to be. This was the determination of parity violation in atoms, which is the reference nowadays. It has been for many, many years. This measurement, I was telling Professor Wieman that is very close to my heart because this is the experiment that I work on my PhD, that I tried to do during my PhD for many years. And I'm sorry to say that we're still miles away from the beautiful result that he was able to obtain. It was the same system, but with the, same measurement, very similar measurement, but with a different system. So it's a very complicated, and it shows how good of an experimentalist Professor Wieman is. Now, besides that, during his extra time, he decided to work on the most important experiment at the time. Everybody in the community recognized it as such, which was the demonstration of a Bose-Einstein condensate. And a few years later, together with Eric Cornell, they were able to demonstrate this new state of matter. So let me just emphasize that again. He was able during his work, as part of his work, he was able to demonstrate a completely new state of matter, which is Bose-Einstein condensate. And for this remarkable result, he was awarded the Nobel Prize in 2001, together with Eric Cornell and Wolfgang Ketterle. So after saying that, I know that I should say many more things about the career of Professor Carl Wieman, but I think that will be just wasting my time. If you can do that during your lifetime, that will be an incredible accomplishment. Um, After earning the Nobel Prize, he changed gears in his career a little bit, and he decided to attack the problem of solving the problem of education, of physics in general, science more in general. And he attacked this problem the same way he did with the precision measurement, using a similar philosophy. And that's the topic of today. So after saying that, I just want to thank again Professor Carl Wieman for agreeing to give us this colloquium, and I'll leave you with Professor Carl Wieman. Thank you very much.
Okay, thank you. It's a pleasure to speak with you today. Let me share my screen here. Yeah, so I'm going to talk about taking a scientific approach to physics education. And what I'll cover today is first just a general introduction of how the brain learns complex thinking like a physicist. And then give you some idea about how we and my group and many others have been applying these ideas in testing them in university classrooms and measuring the results. And then I'm going to focus in tighter, sort of giving you a brief overview, but some of the detailed findings from research in classrooms on what works to improve the learning of physics and why. And this is, if you're an instructor, these are things you can think about using in your own teaching. If you're a student, you can sort of think about how they work to guide your own learning. But before I get into this, I want to just give a little bit of idea of the background, how I got involved in education. And it actually started way before I got the Nobel Prize. But it also didn't start because of teaching students in classes. It really started with my atomic physics research. And there was a puzzle that I saw consistently happening, which is that these new graduate students, they'd had many years of success in their math and physics classes. That's how they became graduate students, able to come and work in my lab. But when they were called upon to actually do physics in the lab, they really didn't seem to know much how to do it. And at first, it seemed like this was just a peculiarity about individual students. But then I came to see that, no, this was really a consistent pattern that happened over and over again. And it wasn't some deficiency in the students, because after just a few years working in my lab, they had turned into expert physicists. And so after seeing this enough times, I decided there was a real fundamental puzzle here about learning. And this was something like 35 years ago. And so I tackled it really as a science problem, looking at the research on how people learn, particularly how they learn physics, and trying to make sense of this behavior. And there was enough research. We've done a lot of research more since then, but there was enough research even by that time that so to digging into this, I could understand this puzzle. There was an explanation to it. It actually made sense that this was happening. It also made me realize there were much more effective ways to teach than what most professors were using in their classrooms. And then it also got me started in doing science education research, doing experiments, collecting data, establishing those basic principles. So very much like physics in a lot of the thinking. But in all of this work, I kind of my central focus has been on what I'll call expertise, thinking like a good scientist, a physicist, or engineer, and how does that kind of thinking develop, and how can we best teach it most effectively? Now, there's actually been sort of major advances in the last couple of decades, giving us new insights on the process for learning and teaching this kind of complex thinking. And we have complementary results from three different areas of research. There's the cognitive psychologists who mostly in the laboratory study basic processes of how people think and learn. There's now increasingly recently brain research looking at how the brain functions. And then there's the work that like I do and other physicists and biologists and so on, which is actually doing research and studies in university science and engineering classrooms and trying things and measuring what works. Now, I'll just say in passing that we have the best data on what are good effective teaching methods from the university settings and with university students. But if you're wondering if these things are generalizable, I think we can be quite confident that what we see at the university applies also at the high school level. But lower than that, I think there are more questions that would come in. So let me talk about what has all this research taught us. And the most basic thing is really rethinking the whole process of how learning happens. And the old and still widely accepted at the university level current model is that we have these student brains and they come into our classrooms and they vary in different ways. And we immerse those brains in knowledge in the teaching. And then that knowledge just soaks into different amounts depending on the condition of those brains. And so with this as the basic model of learning, then the focus at most universities is then on trying to select the best brains, the ones that are going to absorb this knowledge the best, and thinking about what to put in this knowledge soup, what topics to cover at which order and so on. Now, as I say, this model is very widespread and it's been around for a long time, but it's just wrong. The research gives us quite a different picture. And the research tells us that brains aren't these fixed things, that in fact, particularly at the university level, they start out not all that different. But the educational process really transforms the brain. It changes the brain. What it literally does is it rewires how the neurons are hooked up. And this rewiring is in response to intense thinking that is involved in the educational process. And this rewired brain has improved capabilities. And so the process is really much more about developing brains rather than putting knowledge into them. Now, researchers can actually see this now with modern brain imaging. And this is just an example of two people who are in a functional MRI machine and interpreting an X-ray image. And on the right is a brain of a medical student who's just learning how to do this. On the left is an expert radiologist who has many years of practice doing this, and you can see how their brains are being activated in very different ways, and as a result of the training the radiologist has. So the most kind of basic result from this research is that the learning process is really about enhancing the right sort of neuron connections in the brain. And as a sort of fundamental level, what we see is the brain really learns what it practices. And so it's very, very much more like muscle development than people used to think about. And so just as in a muscle, to develop it, you need to use it strenuously over an extended period of time. And so what we see is that that's very much the same in developing the brain, developing its its thinking capabilities, the intensity and type of the mental, in this case, the mental exercise is really critical. And so a lot of what we researchers are doing these days is just learning more effective ways to teach, better ways to have the brain exercise, to develop the new skills we wanted to have. So that's kind of the big picture. Now, let me just kind of go in and give you an example of the kind of work we actually doing in university classrooms and measuring the results. So this is an example, and I could give you many others that are similar, but this is one example that experiment I was somewhat involved with. And it was looking at the learning in a big introductory physics course. And it was a large enough class we could have two sections of the class with 270 students each that very carefully measured the student population was essentially identical between the two. And then these two sections were taught in different ways. The what we call the control section, it was taught by a highly experienced professor who had good student ratings, but he taught a fairly standard lecture approach of talking to the students and they're listening and taking notes. So very much like most university courses in science are taught these days. And then the experimental section, it was taught by someone who was a fairly new PhD, but had been trained in the program I ran in these principles and methods of research-based teaching. And so the two instructors agreed to cover the same material in the same amount of class time, and then gave a surprise quiz to the students in both sections. And this was really targeting just what they learned from class, because they weren't studying for homework or exams or anything during this period. So it was really a measure of how much they learned from these different classroom experiences. Now, I assume you know what the standard lecture looked like, but I'll tell you what happened in the experimental class. So the students first had a short pre-class reading assignment. This really wasn't for them to learn the physics. It was really just sort of basic facts and terminologies that they can gather from a book. They don't need to waste class time telling them that. And then class would be spent with the students having to think about things, being actively answering questions. And so here's an example of a question they were posed, where you have a circuit with light bulbs and a battery, and their students are asked, what's the brightness of bulb 2 going to do when you close that switch? And they have 4 choices here. And we use some technology to make sure every student's involved and the instructor can monitor how the whole student population is. So they use this, each student would have to answer this question. And when this was done, they had a special device, a clicker for that just pushed the button on. Nowadays, it's usually done just with mobile phones, but the same principle where the student has to choose what they think the answer is, select it, and then the instructor's computer records who the student were and what answer they chose. But so they would go in and put an answer, but then they wouldn't be told what the answer was. Instead, they'd be told to discuss with their neighbors in a big lecture hall like this, just be basically students on either side of them, as to what the answer was and why, and then they would have to re-vote. And while they were doing that discussion, the instructor wasn't just standing waiting for them to finish. The instructor would be circulating around, listening in on those conversations, getting little snapshots of what was going on in the student brain. So what aspects of their thinking was like a physicist like we wanted, and what aspects of thinking were confused or wrong. And okay, and so after the second vote, then they demonstrate what actually happens with the light bulb. And then the instructor would have a follow-up summary, which is really giving feedback to the students on which of their models and reasoning were correct and which were incorrect and why. And I emphasize this incorrect because this is something I've learned from cognitive psychologists about what learning really takes place is not when you have a question that you answer correctly. It's when you do something incorrect and you're helped to understand why that was incorrect and how you need to change your thinking. That's really where learning happens. Now, this wasn't all just multiple choice questions like this. For more mathematical topics and many more advanced courses, physics courses, we use worksheets where they actually have to write out things on paper. But the same idea of working together, talking to things, and getting feedback from the instructor. So if you think about what's happening in the students' brains during this activity, they're practicing thinking like physicists. They're having to look at this problem. They're having to choose and apply a conceptual model of how electricity works and apply it in this situation and make predictions. And then they have to critique their own reasoning and that of their fellow students in the discussion. So in terms of the problem's elementary, but in terms of the thinking process, this is, they're really much like physicists. And while they're doing that, they're getting feedback to help improve their thinking. They're getting it from multiple sources. They're getting from the other students. They're getting it from comparing what they're predicted with what actually happens. And they're particularly getting it from the instructor who's now well informed about their thinking. Okay, so that's how the class was taught, but this was part of an experiment comparing the two with it. So how did the two sections compare on this identical quiz? And so here's the results. And you can, with the standard lecture class, the histogram of student scores versus the number of students. You can see the experimental class is much better, higher than the standard lecture class. And in fact, the difference is probably a little more than what you might first appreciate, because on this particular test, random guessing would give a student about 3. And so the amount of learning is really how far above 3 you are. And when you recognize that you realize just how tiny the amount of learning from the lecture is. And there's many other examples we have to showing this similar thing. But in addition, want to emphasize how the experimental class didn't just improve the learning for the top students or the weak students. It really improved the entire distribution moved up. So this is really shows it's better learning for the entire population of students. Okay, so that's an example from an introductory course, and most of the education research in physics has been done in introductory courses just because that's where most of the students are and the teaching. But in the last several years, there's been a lot more work, particularly in my group, looking at more advanced courses and showing that these same basic principles if as implemented in more advanced undergraduate physics courses, also lead to considerable improvement in learning. And in fact, now we've transformed the teaching of almost all the Stanford undergraduate physics courses now have been transformed to this kind of research-based, what we call active learning, where students, as you can see here, they're, the classes are much smaller, the much more mathematical. Students are working on worksheets, completing these activities during class, talking to each other in small groups, and being monitored by the instructor. And this method's even been applied to graduate courses with good success. So as a sort of general rule, there's kind of a general structure of these active learning classes that we've seen works pretty well for almost any subject in science, actually, and certainly in physics, and any level and most any class size. And the structure is sort of the students usually have some sort of modest preparation before class, and then the instructor kind of introduces the task for the day, and then the students are working on the activity, completing separate parts here, figuring out, making decisions, completing answers, and so on, while the instructor is circulating and monitoring how they're doing. And the students might do that for 10 or 15 minutes and then come to a reasonable stopping point, at which the time the instructor will pull the whole class back together and give feedback to the whole class, answer questions, make sure everybody's kind of up to the same point, and then the students will go back to continuing working through the activity. And really the essential features of this teaching are really the students are busy thinking. They're practicing the reasoning you want them to learn and the application of the knowledge that you want them to acquire. And the instructor is much more knowledgeable about that thinking, so is able to give more effective teaching and feedback, targeting where the students most need it. So these are just a couple of examples. There's almost 1,000 research studies I was able to dig up, actually, across undergraduate science and engineering, comparing the traditional lecture with these kind of research-based teaching. And it shows the research-based active learning consistently showing greater learning and consistently lower failure and dropout rates. Now, there's been another aspect of this problem, though, that my group has been working on the last few years, and that's if you look at the results we got from this in this experiment I showed you, there's still a bunch of students down here who they're better than in the regular class, but they're still not doing very well. And so what we'd really like to move is have everyone pile up here at the top. And so I got particularly interested in this after I went to Stanford, because this kind of distribution was also seen at Stanford. There were some students doing very well, but also in the introductory physics classes, always a significant number were doing poorly. But Stanford, as you probably know, is a very elite selective institution. So I was struck by thinking, gee, these students are remarkable by many measures. How come they still are doing poorly in introductory physics? And so we collected lots of data, looking at lots of possible factors for this, for why these students are doing badly, and ruled out a lot of things. But what we found out was that the difference in course grades and the spread and the distribution was almost entirely due to the prior preparation. That we had a measure of students' incoming preparation in physics, which was a very good predictor of how well they were going to do at the end of this course, a semester later. And we collaborated with people collecting similar data from other universities with very different student populations, and we got very much the same thing. And so what we came to realize was that the real problem was that the instructors implicitly, not sort of intentionally, but implicitly, they were really optimizing the coverage and pace for the students in the kind of the top third most well-prepared, most educationally privileged, and in the process were really sacrificing those students who came from high schools where they didn't get much physics or not nearly as good physics. And so we came to appreciate that it really wasn't a problem with the fundamental characteristics of the students. It was just the teaching wasn't appropriate for the level they were at. And so they came to decide that really what one needs to match the curriculum more appropriately to the students and their background, and many more students could succeed. And we've been doing experiments on trying to do that, which are giving pretty encouraging results. Okay, so I want to move on to getting into sort of details about research findings and things you can actually use in teaching beyond what I've already talked about. And so this figure is kind of my summary of all the research in physics and education and learning. And at the heart is this idea of the student learning happens because of the students practicing, and particularly practicing solving problems, because really being a good physicist is all about solving physics problems. And so they have to be practicing solving physics problems, and they've got to do that with good feedback to help them improve. And what we know about is good feedback is that it needs to be timely and specific and actionable so that they help improve. But then there's a whole bunch of factors listed shown at the top here that go into the design of the optimum design of the practice problems they're having to do. And then there's some research at the bottom on sort of details about how to effectively implement these in the classroom setting. And so I'm going to just touch on each of these a little bit, but I just want to make the point that I think this really, what's contained in this figure really defines teaching expertise in a way you couldn't have done, 10 or 15 years ago. And it really allows one to think about what it means to be a good teacher, what practices you need to know and apply in that actually will produce more learning in a predictable way. Okay, so let me go through and talk about some of these things in the design. So first, there's the disciplinary expertise, and that you need to think about what it is, what's the nature of the thinking you want them to practice that, makes it special for physics. And here I'm going to rely on a bunch of research my own group has been done on the nature of expertise, in particular, how experts across science, engineering, and even some in medicine, we looked at how they solve authentic problems in their discipline. And what we found was that the problem-solving process was really defined by a set of decisions they would make. And the surprising aspect was that although we were looking across many different disciplines, we found the same set of decisions, or actually 29 of them, came up over and over again that almost all these experts were using in their problem-solving process. And, that may sound crazy when you think about such a range of engineering and science until you actually look at what those decisions are. And I'll just give you examples. They're, for example, deciding and faced with a problem, what concepts and models are relevant, deciding what information's relevant, irrelevant, what's needed, deciding how to find that information, deciding what approximations and simplifications are appropriate, deciding how to break the problem down into parts, etc. And so once you see the nature of it, you can realize, oh, okay, yeah, I can understand that those are going to apply across a whole range of technical problems. But the other thing I want to emphasize is although the decisions are the same across different disciplines, the actual making of the decisions, how you need to make the decision well, that always requires specialized disciplinary knowledge, specialized to the context of the problem. And so that what that means in terms of learning also in the practice of what students are doing is you need to give them, they need to learn the information in such a way that it's organized around how to apply that to actually make decisions. And so this means that, the learning good expert thinking, thinking how to solve physics problems like a physicist, more like a physicist, really requires practice making problem solving decisions in an authentic problem context and sort of practice applying the knowledge and reasoning of a physicist to do that. Now, because I think it's really important that in teaching, we think about actually teaching students to practice making these decisions, and students who are learning need to think about explicitly thinking about their decisions and their problem solving process. So I'm just going to give you a minute to read through this set of decisions here for the whole set, just so you have a better example. So I'll just stop talking here for a minute while you can read. Okay, so what I would argue is that the learning process really needs to involve the practicing making these decisions in some real context and gaining the physics knowledge one needs to make those decisions well. But one thing I want to emphasize is how in teaching, and you look at the typical homework and exam problems that are given to students in physics courses, and we've studied this, we see that almost all these decisions are actually removed from the typical problems. If you think about problems that you might see in an exam, and they're always told what to assume. The problem's broken down into pieces for them. They're given all the information they need and only that information, all these things that are really essential for real authentic problem solving. And so what we've seen in studies is that the result of this is students learn a bunch of information, but they're really poor at knowing how to use that information in meaningful ways, solving problems. So that's really the nature of the disciplinary expertise that goes into what they're practicing. Now, let me talk about just very briefly about the importance of prior knowledge and experience and motivation. So the prior knowledge is this practice task. They need to be challenging and difficult, but still possible for students to achieve. And so you've got to match the demands of the problem to connect up and build on the students' prior knowledge and to give them the right level of challenge. And the second thing is motivation. And like prior knowledge, motivation is quite variable across students, which makes it more challenging to make it work for all of them at once. But I think sometimes we sort of neglect motivation at the university level, but that's really a mistake because motivation is really critical for people learning. And some of the things we know about enhancing motivation is try and find an interesting, meaningful context for the material. So it's not just abstract, meaningless, artificial physics problems. It actually, people can see why these ideas would be useful, how you'd apply them. And it's also important for the learner to know how to learn or believe that they can learn the material and how to learn that, and they get a sense of accomplishment as they succeed. That's highly motivating. So those are just a couple of quick comments there. I want to move on to, there's some basic constraints about how the brain works. It's really critical for teaching, but not widely recognized at all. And the most important is sort of how the memory works. And if you think about memory, there's actually two parts to it. There's what is called the long-term memory, and this is what we think of most times when we use the term memory. This has a very large capacity and it lasts for very long periods of time, years, decades, etc. But in addition to this long-term memory, there's something called the short-term working memory. And this is really an information buffer that information ideas have to go through before they can be processed and get into long-term memory. But the working memory, it's profoundly different. First, it operates on time scales of minutes, quite much shorter. But most importantly, it actually has a tiny capacity. It's sort of 5 to 7 items that it can hold at once. So it's really what the brain can pay attention to at one time. And this capacity, this limited capacity, is very important because what it means is that if you pay attention or see some new item, it pushes something out of the working memory. And so what got pushed out doesn't get processed and doesn't get into long-term memory. And so this has a tremendous implications for learning and teaching because it means that each additional item, new thing that's presented has a real cost. It uses up some of this precious working memory space. And so the most serious aspect that shows up in teaching is split attention, where students are checking email, looking at their phones, whatever, even worse online because they've got more things on the screen that they can be splitting their attention to it. Because as you split attention, you're paying attention to other things that's using up a whole bunch of your working memory. And so it's just a disaster for learning. And it's even worse because people don't realize how big a disaster it is. But there's also things that the instructors can do that use up this precious working memory unnecessarily. So using a lot of jargon that's unfamiliar to students. Each of those new terms uses up this 20% of working memory, and just presenting many new topics, that are typical in a typical lecture. It's just way more than the brain can pay attention to. And even things like making pictures kind of fancier with attractive little features or interesting little side notes or jokes that actually take up students' attention, they actually have shown to hurt learning. Okay, let me move on to some things about research on implementation. So first, implementing these things, you have good design tasks, but you also have to have clear deliverables, things the student has to complete in class and out of class that are having them practice what you want them to do, that they have to be some level of accountability for. And then there's social learning. I sort of mentioned in passing all of these things, that students are working in small groups. And it turns out there's a real learning benefit to that. The group optimum group size is 3 or 4 students, incidentally. But a lot of times instructors are surprised at this because they think, how can it be that talking to a fellow student is better, spending that time better than hearing me, the expert instructor, explain something? You know, why? But we have data showing that's actually true. And there's also some basic reasons, principles, so you can understand that. First is that your fellow students, they can't give you as all the extensive feedback that an instructor can, but they can give a lot of individualized feedback, helping students out on particular points or some small misunderstanding that, you know, no instructor has the time to cover all the students in the class. Whereas when you're talking with a group of fellow students, you can get that feedback targeted right away. But then there's another kind of more interesting benefit, which is that it's a well-studied process, that the process actually of teaching somebody or explaining something to somebody else actually triggers some unique cognitive processing that the brain sort of has reserved for social interactions. And so it's been shown how this process of teaching somebody or planning to teach even to somebody causes people to think about the material in a different way that actually produces more learning than if they just try and study it on their own. Okay, so that's I'm going to start finishing up here. Covered lots of different things, but the conclusion is just that research shows really at this point what's good teaching design and implementation, and that produces better learning than traditional lectures. And we understand really why at the level of basic principles. Now, before I open this to questions, I'm going to pose a question that I've often get, and so I'll jump in ahead of time, which is, many times I give this talk and instructors are there and they kind of get this question one form or another with, well, traditional lectures can't be as bad as I'm claiming because look at us university professors who were taught that way and how successful we were. And my answer to that really is that that's exactly the same reasoning that was used to make bloodletting the medical treatment of choice for 2,000 years. And just as with medicine, we got past the logic of bloodletting by having proper science where you had proper comparison groups, and so these professors who were taught by lectures, yes, they learned something, but they probably would have learned, if they had a comparison group, they would have learned more if they by research-based teaching. So here, I'll finish here. I'll make sure my slides are available if people want to review them. But here are some of my favorite references, some books covering these ideas here. And then that the CWSEI website or resources on implementing particular practices, short guides, and so on. So thank you for your attention.
Thank you very much. That was excellent. And yeah, having the slides will be fantastic. The talk is anyway recorded for whoever wants to see it again. But having those resources available will be fantastic for many people. So the talk is now open for questions. I ask anybody that has questions to put them on the chat on the YouTube on the site, and I'll be relaying them to Professor Wieman. While they start putting some questions, let me start by a question I have. So in order to learn something, one has to repeat it. When I used to study dates for history, I would repeat the same year over and over until it goes to the long-term memory. So my question is it known about how many repetitions one has to do to get something way on into the long-term memory? And also, if there is a requirement on the delay of the repetitions, because I fear that one can try to explain something to a student and you can tell him that thing once, and then you can even repeat it, but you repeat it, for example, the next day, and then you repeat it again over 1 month. And I'm guessing that if they are too spaced, then repetition doesn't work. It has to be probably repetition, but within some minimum delay. Is this known?
So people have studied this, particularly for just kind of memorizing basic facts or words in a foreign language, things like that, where it's just simple memorization. This has been very extensively studied, and there's a few things well known on this. The first is you want spaced repetition. And so you need things, if you want to have long-term retention, you need to repeat the memorization process spaced out in time, and over time making that spacing longer and longer seems to help. So it sort of starts out shorter and then increases. The other things that are important is when you're trying to remember something, having it interleaved with other things. So rather than, this is trying to remember a set of words, rather than just those same words over and over, having it interleaved with other things seems to be beneficial. But probably the most important thing is what they call the testing effect, whereas you don't just read over the things, you really test yourself on trying to remember it. Or in physics terms, it would be really, you want the student to try and think through, the understanding on their own. And then if they might get feedback after that, but their process needs to be really trying to remember it, trying to understand it on their own, and then going back and reviewing that. But that additional processing is really critical element. But you're then also right about longer term. You have to do that repeatedly. So.
Okay, thank you very much. So there is one question here that says, is it possible to de-learn something that was saved in the long-term memory?
Yeah, so this is an interesting question because we talk about misconceptions, basic ideas about physics that people have wrong to start with, and how you can correct those. I mean, a common one is the idea that heavy things fall faster than light objects, and it turns out people can de-learn those things. They can learn it correctly, but it can be remarkably difficult to sort of, and this is where you have to kind of recognize prior knowledge, because some prior knowledge is useful and you build on it and show students how to use it. Other prior knowledge is just wrong and you have to have them remove it and modify it. And so it can be done, but it is quite difficult. You have to have the person really focusing on their not just whether they're right or wrong, but the thinking process they're using, and getting them to really re-examine and change that thinking process. And oftentimes you have to do that repeatedly for sort of strong misconceptions to get them to change. And it can be remarkably difficult actually to change some deeply held thoughts.
Okay, thank you. There's another question says that says, what do you think about simplifying ideas to teach something for the first time? For example, saying that anatomy is like the solar system. It seems that simplification is intrinsic to teaching, but simplification is also dangerous.
Yeah, so this really, I would say, goes to use of analogies. And analogies are very powerful way of teaching things and learning things. And there's some arguments made that people's thinking is almost entirely based around using analogies, where you take something you already know and you kind of adapt that and think about how to adapt that for understanding something new. And so it is, you can understand why it's so powerful, because it is taking and having to do the working memory comes in here, because you're taking some complex, an analogy, you're taking some complex new relationship and you're mapping it onto some known relationship already known to the learner, to help them understand that. And so that is a very powerful aid in learning. But then there's also the point of the danger of you're using some analogy which is never completely correct, and so they can then be confused of carrying the the solar system model of the atom too far. And so what's been shown is much more effective than just having a single analogy, is actually to have multiple analogies, like two analogies for the same thing, but two different analogies that help the learner then, by that comparison, they can recognize what are the features of the analogy, do they carry over, and then what are the feature of the analogies that are different. And so so that there's some really nice research been done by a friend of mine showing how multiple analogies are much more powerful for teaching, and that's multiple comparisons are much more powerful in teaching than individual ones, just because of this idea of they're never perfect, and to understand the difference between the reality and your analogy. But having said that, I also know from trying to teach with analogies, it can be really hard to come up with multiple good analogies for particular situations. So but that's a teaching challenge.
Okay, so another question, in the active learning model, what role the homework plays?
Boy, all of these are really good questions. So the role of homework, first, I have to say that the research on this is really quite limited, which is kind of surprising when you think about all the, all the different things people have studied, that homework is such an important part of the teaching that it hasn't gotten a lot more research. But there is some saying graded homework where they have feedback on it does contribute to learning. And I look at it as, for the active learning, it's just continuing this process that the students are having to, in class, they're practicing the thinking and getting feedback on that. And then the homework is just an opportunity for them to, you want them to just extend that thinking, to continue that practice in thinking about the ideas. And so it should be fairly seamlessly connected between the homework going beyond what they've done in class. But one of the benefits to active learning is that because students are learning more from class, they actually have greater capabilities to tackle homework that's maybe not exactly the same as they covered in class, but they got enough thinking practice in class, they can go and cover some new things. And so you can kind of extend coverage of the material actually by putting somewhat new material in the homework, going beyond the thinking they practice, just because they now have the greater capability to do more challenging, novel homework problems.
So let me rescue one comment that I'm now applying to my own personal classes from one of your articles that said that one should start paying a little bit more attention to the homework than to what happens in class. That one should concentrate on what kind of homeworks one leaves. And as a follow-up of this question, would you recommend, what would be your recommendation to give a homework that continues on what you taught, or homework that prepares them for the next lecture? What would be more important?
So I tend to think it's more important to continue with what they've had, and it's just because you can't really expect, or you're expecting too much if you expect the students to learn a bunch of new things from the homework. That's just, I look at that as that's just too hard. The hard stuff, if you do it in class, they've got their fellow students to help them, they've got the instructor to provide guidance, and so that just makes it much more new difficult material much more accessible to them. And then when they've had that help, you can give them much more challenging homework problems that they're now more prepared to do. And so I tend to see the homework as more useful in practice and extension of what you've covered in class, as opposed to preparing for the next class. I tend to think the best use of we do give things for preparing for the next class, but those, I tend to think that's most beneficial to just make that as basic factual information, like terminology, some experimental result that somebody got, that you want to talk about its importance and so on. But it's not complex physics ideas. But it's a body of knowledge that they can easily acquire. But the hard stuff, safe for class and homework.
I see. Okay. Another question says, motivating students is increasingly difficult. Could you give us, additional suggestions to improve motivation?
I wish I could. I know this, like I say, the challenge is really finding, like I say, sort of putting the material in a context that student sees as meaningful, as, based on their previous experience in life, based on their planned careers and so on, that they see, oh, this is interesting and useful. And, it's easy to say that. It's hard to come up with, cases that do that, particularly for when you have students who have a whole range of different experiences and interests to do that. But, that's the one starting point, and it takes a little thought, but usually once you get used to it, it's not that hard to come up with almost any pretty abstract thing you can think about, putting that in some meaningful, applicable context for it. And so that's important. But the other thing is, the other aspect of this is really to make sure that you get plenty of opportunity for students to recognize that they're learning things. And so this is a problem if you give really hard exams that do a great job of sorting the students, but the average student is, getting 50% or lower. then they're really feeling like they're not really learning anything, not learning what they were supposed to, as opposed to you could give the same student an exam which covered a lot of things that maybe don't seem that hard, but are new things they will have learned, and they can and makes them appreciate, oh, I'm really learning meaningful things in this class. And that tends to be much more motivating for people. But that's about all I can say. I recognize that it's not easy.
So along the same lines, there's two ways to motivate people, the carrot and the whip, right?
Yeah.
Has it been studied which one works best?
It has been, and the carrot works a lot better. So we talk about internal and external motivations, and so the internal motivations is because they think it's interesting and useful, and they want to learn it for their own sake. The external is, okay, you got to do this because you'll get a bad grade if you don't do it, and what the problem with that is, it can be successful in the short run, but it's almost always not very successful in the long run, in that they kind of, okay, I'm learning this because I'm gonna flunk if I don't, but as soon as I get through the course, now I don't want to ever think about this again, because I was whipped into it. And so, but I do kind of recognize that we have a system of grades or marks that the students have gotten used to. And so you do sort of have to just recognize that that's part of the system that they're accustomed to. And so you want to make your external, the whip, the grades that kind of consistent with what you want them to be doing for their own sake. But it's always better if you can convince them they want to do it, as opposed to you're making them do it.
So one question about the methodology. In physics, it is common to compare systems, control, and experimental, since we're dealing with inanimate objects, atom gases,
Yeah.
etc. Why carry out the same treatment in the case of people?
So, I mean, I look at this as you always have to try and think carefully about good controls, whether it's in physics or biology or teaching. And so, in the best controls are defined as you work very hard to try and design the experiment so you've got populations that are as identical as possible, getting different kinds of teaching treatments, and what they're subjected to are sort of as similar as possible, just because that's the only way you can get meaningful results. But the research requires spending a lot of time thinking about exactly what comparisons you're going to be making and what kind of control populations you can get.
Okay. Next one is, you explained us the research-based methods or best teaching practices, but do you have any suggestions to improve learning for the students who are still attending traditional lectures?
That's hard, but in fact, yeah, what you have to think of as a student is, what really counts is your mental what's going on in your mind. And so you need to really be thinking about very actively processing the material. And so what some guidelines there is, kind of think about how you could explain this, the lecture, they're telling you things, think about how you could explain this to someone else. And so you have to kind of process the ideas and think about that. You have to think about when they're telling you new information. Almost everything in physics was developed, techniques and so on were developed to make decisions. And so it helps as you're getting new information to also kind of be actively thinking about, okay, this knowledge, this is being presented, where would that be used to make decisions in physics, and what other places, what other contexts could that be where that could be applied? And so you be doing a lot of kind of extra thinking during the lecture where you're trying to do kind of additional processing, and frankly, that means you're going to miss some of the things that are told because there's just too much information. There's, this, we talk about cognitive overload, but at least you'll get more benefit from that, from what you are able to kind of actively process.
Okay. And next question is, from your presentation, it is clear that the learning process transforms the brain. In terms of the time required to obtain a bachelor's degree in engineering or physics, is 4 years optimal?
So I don't think there's any real answer to that question. People have done some degree of studies of how many years of kind of intense thinking practice are necessary to become a high level expert in a subject. And I've sort of looked at how many hours, and they come out with something approaching 10,000, and that's kind of a rough approximation, but it's starting point. And I've actually looked at how many hours of kind of thinking, studying somebody does if they go through an undergraduate, graduate school, and a postdoc, and it comes out to be pretty much in the neighborhood of 10,000 hours. And so it says, to me, that says that that's not a crazy amount of time, or that it's sort of what the system we have now provides people with that kind of level, what they need. Now, whether an undergraduate degree should take a year more or a year less, and you shift that learning around, I don't think there's any real answer to that, but I think it's really kind of the total amount of time to become an expert. You can sort of see what's required, but the exact distribution and that determines, what you expect what level of capability you expect people to have with an undergraduate degree, and that's a pretty arbitrary thing to me. So
I see. The next question, what do you think is more important when learning something in physics? Learning the physical interpretation before doing the calculus, or learning the mathematical methods to solve the problem?
So this is a place where there's very limited research, but I would say it's learning the physics concepts before you learn where you think of the mathematics as a tool to do physics with, as opposed to learning the mathematics first, because then you sort of have a tool, but you don't know what to do with it, and tools that you don't know what to do with aren't very useful. So I think I would argue kind of learning the physical processes and physics questions that you then learn the mathematics you need to use with that to solve physics decisions with is likely better. But there's been a little bit of research on that in introductory physics levels, but not very extensive. But I think just kind of my thinking about what's involved in the nature of the expertise would suggest that I'm probably right.
So the next question is, you explained the short-term memory role, but how long would it take for the information be in the long-term memory? Or is there an efficient way to channel the information to the long-term memory?
The so there's the time it takes is not very well defined, is the answer for getting things from short-term to long-term memory, but it's really the efficient way is really it involves the mental processing you're doing with that information. So you're having to think about it, think about applying it, think how it connects up with other things you already know. And it's that processing step that moves things from the short-term memory into long-term memory. And so that's what you have to do to kind of do it efficiently or really at all. And that's the same thing that I was saying is how a student can get as much benefit as possible out of a lecture is really to try and do the mental processing of that in different ways.
Okay. The next question says, in your opinion, what will be the direction of physics in the next 10 to 15 years? It would be the same way about how can science be learned, or how can we implement the technology nowadays?
So I'm not sure I understand the question. Is it about physics or is it about learning here?
Yeah, I'm not sure either. Let me read it again. In your opinion, what will be the direction of physics in the next 10 to 15 years? It would be the same way about how can science be learned, or how can we implement the technology? Let's I'm not really sure. Let's talk about physics. No, that takes us a little bit away from the topic.
So yeah, I mean the future of physics, I'm not going to make predictions on. That's that way outside of my expertise. The future of learning, this brings up the ideas of technology, and lots of people are thinking about artificial intelligence and how it's going to affect things. And I suspect it's going to be profound. I think we're just still struggling to understand how to best to use it and what it can and can't do in terms of teaching. But I think it's likely it'll change things quite a bit. I think it really raises very fundamental questions. I mean, these new large language models and artificial intelligence, it really raises very fundamental questions about what it's going to mean to be an educated person, because so much of what we do with education is teaching people how to, learn things that they can do, where now so much of that they can just ask the computer. And people will be just relying on asking computer. And so then what exactly is going to be the most effective, meaningful education? And I don't know. It's a profound question, I think.
So apparently there is, I don't see more questions. If anybody has any other question, you can put it there. Let me then ask probably a final question if there is no other. That may be a good motivation for the students attending the lecture. So in your opinion on what you have seen, do you think all of the students have about the same hope in being good at physics? Because it's clear that in some courses, one can see a very talented student and you can see a wide range of them. But assuming that all of them do their part, that they are motivated and they work, how much variation would you think you would have among the students in a course?
So, that's a difficult question to answer. But what I can say is, the more we've dug into this with research, the more we see that the student differences are being determined by what their prior educational experiences were, as opposed to kind of any measures we can have of sort of fundamental capabilities. And so, you know, from my perspective, I've come away sort of that there's realistically there's no way to predict who could be a good physicist or not. And so we have to assume that every student could be if they had the right educational experience, and then provide that to them. And there are certainly going to be differences, but I think you know the evidence would say that you really can't predict that in terms of any fundamental thing when everything you see depends so much on who had what teacher previously. You just have to assume, okay, if I teach this student well, they can be successful. So
All right. So it looks like there are no more questions on the chat. So
well,
with that, we thank you a lot about the really, really interesting question. I think this gives us all some food for thought. And I really, really hope that in our university, we'll start implementing the same methods that you already told us you are using very successfully at Stanford University and other places. So I hope that this is a message that we all take home. And we thank you again for this really, really interesting colloquium.
well, thank you. And I'll compliment you on a really great set of interesting questions. Better than usual. So
thank you very much.
It's been a pleasure. Okay, goodbye.
So we can stop the